Hello students, in this lecture we will cover linear regression. So linear regression is the simplest model in machine learning. To apply linear regression, our dataset must meet three conditions. Number one, there must be at least one predictor variable in the dataset. Second, there must be exactly one target variable in the dataset. Number three, the target variable must be a numeric variable and not a categorical variable. Let us look at two example scenarios where linear regression can be applied. So, in the first scenario, we want to predict the price of the house based on the size of the house, the number of bedrooms in the house, and the age of the house. So the price of the house is the target variable, and these three are the predictor variables. We represent the target variable with a y and the predictor variable with an x. Now because there are multiple predictor variables, we can use subscripts to distinguish them. In the second scenario, we want to predict the test score of a student based on the number of hours studied by the student. So the test score is the target variable and the number of hours studied is the predictor variables. Now we want to verify whether these two scenarios meet the above three conditions. So let's check. For the first scenario, there are three predictor variables. So the first condition of having one or more predictor variables is satisfied. The second condition is to have exactly one target variable, and we have exactly one target variable, which is the price of the house. So this condition is also satisfied. So the third condition is that the target variable must be a numeric variable. The price of the house is a numeric variable. If instead of the price of the house, we were predicting the condition of the house, whether it is good or bad, then we would be predicting a binary variable or a categorical variable and not a numeric variable, and then this condition would be unsatisfied and linear regression would not be applicable. But since that is not the case, since the target variable is a numeric variable, the third condition is also satisfied. Now look at the second scenario. There is one predictor variable. So this condition is again satisfied. There is exactly one target variable. So this condition is also satisfied. And the target variable is the student's test score. Test score is a numeric variable. So this condition of that the target variable must be numeric is also satisfied. If instead of the test score we were predicting whether the student passes or fails, then we would be predicting a categorical variable and linear regression would not be applicable. We want to write the target variable as a function of the predictor variables. That means we want to obtain an equation in which if we plug in the values of the predictor variables, we get the value of the target variable. So in case there is only one predictor variable, then the target variable will be written as a function of the predictor variable in this form. This is the target variable and this is the predictor variable, and there are two additional constants added to make this equation. So if we know the values of beta 0 and beta 1, then we can predict y for any x. To make sense of this, let's get back to the scenario in which we were predicting the test score of a student based on the number of hours he studied. So, y would represent the test score and x would be the number of hours. So if we know the values of beta 0 and beta 1, then we can find the test score of any student given the number of hours he has studied. Now, in case there are two predictor variables, then the function can be obtained by extending the previous function by adding this term. And in case there are three predictor variables, then the function can be obtained by adding this term to this function. To make sense of this function or this equation, let's consider the other scenario in which we were predicting the house price based on the size, the number of bedrooms, and the area of the house. So suppose that x1 represents the size of the house, x2 could represent the bedroom numbers, the number of bedrooms, and x3 could represent the area of the house, and then y would represent the price of the house. So given any values of the size, bedroom, and area of a house, if we know the values of these four constants, we can calculate the price of the house. So this is the equation of linear regression when there are three predictor values, when there are three predictor variables, and we can extend this equation to n predictor variables for n number of predictor variables and write it as follows. You can use this generic equation to obtain the equation for any specific number of predictor variables for linear regression. The equation of line is the basis or the foundational concept for linear regression. So, this is the basic form of the equation of line. Here, y and x represent the point on the line, whereas c and m are two constants that define the line. M is called the slope of the line and c is called the intercept of the line. The slope of the line means the steepness of the line or the inclination of the line. To understand the slope, let's move towards this plot. I have plotted three lines here. If you look at the green line, you can see that it is equally inclined towards both the x-axis and the y-axis. What I mean by that is this angle and this angle both are equal. The slope of such a line that is equally inclined towards both axes is 1. Now, if we incline this line more towards the x-axis, its slope will decrease. You can check that the slope of the red line is 1 by 2. Similarly, if we incline the green line more towards the y-axis, the slope will increase. So this is what slope measures, the inclination towards the axis. The second constant here is the intercept of the line. The intercept means the point at which the line intersects the y-axis. To understand that, look at this plot. There are three lines. The green line and the red line both intersect the y-axis at point y is equal to 0. So the intercept of both the green and red lines is 0. Whereas the blue line This line intersects the y-axis at y is equal to 2. So the intercept of the blue line is 2. Now let's make a basic line from this equation. We set the intercept c to 0 and m to 1. So we get this equation, y is equal to x. This is the equation of this green line. Now, if we change the slope to 1 by 2, we get this equation. This is the equation of the red line. Now, if we change the intercept to 2, we get this line. And this is the equation of the blue line. So, the point here is that by modifying the slope and the intercept, by modifying these two constants, we can create any line in the plane. The type of linear regression in which there is only one predictor variable is called simple linear regression. This is the equation of simple linear regression. If we look closely, we will see that this is actually the equation of line, where beta 1 is the slope of the line, which we represented with an m, and beta 0 is actually the intercept of the line, which we represented with a c. Now coming back to the previous problem, where we wanted to calculate or predict the test score of a student based on the number of hours he studied. This is a data set for that problem. The number of hours studied by the student is the predictor variable, and the test score is the target variable. We start by plotting this data set on a plane. We plot the predictor variable on the horizontal x-axis and the target variable on the vertical y-axis. This type of plot of data points of two numeric variables is called the scatter plot. Now, from this scatter plot, we can observe that as the predictor variable increases, the target variable is also increasing. This type of relationship where one variable increases with the other variable is called positive linear relationship. The goal of simple linear regression is to find a line that is closest to all these points, a line that will move through this plot and that will have minimum distance to all these points. So as we saw that finding a line is simply finding the slope and intercept constants. All we need to do is we need to find the values of beta 0 and beta 1 that define the line that best fits these points. Here I have plotted three different lines on the data set: the green line, the red line, and the blue line. And these are the three equations of the lines. Each of the three equations was derived by selecting the values of beta 0 and beta 1 and putting in this equation. The first two equations, the blue one and the red one, I formed these two equations by picking the values of beta 0 and beta 1 by myself, whereas I obtained the green lines equation through simple linear regression. And if we see from the plots, we can see that the blue line is far away from the data points, so it is not a good fit. The red line is close to only one point, whereas the green line is close to all points. In fact, because the green line was obtained through simple linear regression, it is the closest possible line to all the data points in the data set. a better line is not possible. We have obtained this equation of simple linear regression from this dataset. In the language of machine learning, we have trained the simple linear regression model on this dataset. In real world, we will get cases that are not part of our training dataset. For example, a student might say, hey, I studied 5.5 hours, predict my test score. So we can simply plug in 5.5 in our model and we will get 74.7. So we can tell him your test score will be 74.7. Another one says, I did not study at all. What will be my test score? So we can plug in 0 in his study hours and get 42.8 as his test score. So this ability of the model to work on test cases that were not part of the training data is called generalization or generalizability.